Our first problem is this. Jacky invested $150 at the end of every month for 3 years. The interest rate was 3.5% compounded monthly. How much will Jacky have in the account at the end of 3 years? What will be the interest earned? It is important to note that this annuity is ordinary because the payments are happening at the end of each month. Also, this annuity is simple because the payments are happening every month and the rate is also compounded monthly. Because the frequency of payments coincides with the frequency of rate compounding, we have simple annuity. Thus, we have simple ordinary annuity. Now, we need future value for this annuity. The reason we have future value here is because our payments come first, and that's accumulation process, which leads to the accumulation of amount. Future value formula for simple ordinary annuity is this. Future value equals to PMT, which is the periodic payment, times this fraction. In the numerator, we have 1 plus I is the periodic payment, n is the total number of periods, and n is the exponent here, minus 1. We'll divide here by the periodic payment. Let's use this formula. Future value equals to payment, which is $150, times this fraction, 1 plus periodic rate is 0.035 over 12, because nominal rate here is 3.5 and it compounds 12 times per year. Total number of periods is 12 times 3 because there are 12 times the rate compounds per year and there are 3 years, minus 1, and we divide again by 0.035 divided by 12. Now we'll compute this future value. 5,684.96. In order to find interest, we'll take future value, because future value contains all interest, and we'll subtract all payments combined, which is PMT times n. This results in future value, which is 5,684.96 minus all payments combined, which is $150 times 12, because there are 12 payments per year, times 3 years. This equals to 284.96. Thus, we found our answers. Future value for this annuity is 5,684.96 and interest is 284.96. Let's now solve this problem with Excel. We have all the values inputted here and we'll need to find future value. We'll use FV function in Excel. Keep in mind that this FV function is designed for simple annuities. If you have a general annuity, you will need to convert the rate first. But in this case, we have a simple annuity. So first comes the rate. This rate in Excel is periodic rate. So we need to take nominal rate in B3 and divide by total number of periods in B2. Then comes number of periods, which means total number of periods in this annuity. To find it, we'll take B2 and we'll multiply that by the term, which is in B4. Thus, we'll find total number of periods. Payment here is in B1. Then comes present value. In this annuity, there is no present value, which means that we do not invest any money in this annuity in the beginning. We only have periodic payments. Therefore, present value is 0. Then comes type of annuity. This annuity is ordinary. So payments are happening at the end of the period, and that's what we'll select. If we press enter, the answer will be negative. The reason why we have negative answer is because payments here are positive. If we want this to be reported as a positive number, we need to change payments to negative payments, which means that the payments will become amount outgoing so that the future value will become amount incoming. The result here is 5,684.96, which exactly is the same answer as we got using algebra. Now we'll use Excel to compute interest. This is very simple. So you'll take that future value and you will subtract all payments combined, which you'll find in brackets. So you'll open the bracket, then we'll take our payment in B1 times 12, how many times per year we have those payments, and then we'll multiply that by 3 years. I'll remind that compounding frequency here is the same as payment frequency in this problem. Here we go. The interest is 284.96, exactly the same answer as we got with algebra. So now let's continue to the next problem. This problem reads, how many whole and partial payments and how much time does it take to accumulate $50,000 if $600 is invested at the end of every month at 3% compounded daily? In this problem, we need to notice several important things. First of all, this problem is about future value because we have accumulation process here. $50,000 is the future value. Second thing is that we have payments which are made at the end of every month. Because the payments are made at the end of every month, this is an ordinary annuity. However, we need also to notice that 3% is compounded daily, whereas payments are at the end of every month, which makes this annuity general. The reason it is general is because payments are 12 times per year, but the rate is compounded 365 times per year. So we'll need to convert the rate to solve this problem when we apply our formula for future value of annuity. Now let's remind ourselves how we can get that formula. If we have a formula sheet ready to go, that's good. We can take that formula from a formula sheet. However, if we do not have a formula sheet, we always can get that formula. So let's start actually with the formula for future value. So formula for future value is future value equals to PMT. Then we have this fraction, which is 1 plus I exponent n minus 1 divided by I. Now we want to get to n. That's because we need formula for n. How do we do that? Well, we'll take future value, divide by PMT, then we'll multiply by I, then we'll move this 1 to the left side, and on the right side we'll have 1 plus I exponent n. Now we'll use logarithms both on left side and on the right side. And when we use logarithms, we'll apply logarithm rule so that n comes in front of the logarithm as multiplication. So we'll have logarithm future value divided by PMT times I plus 1. And here on the right side, it will be n times logarithm 1 plus I. From here, we can get that formula for n. So this is the fraction. Logarithm is in the numerator of this fraction times I plus 1. And also logarithm 1 plus I is going to be in the denominator. That's the formula, which usually you will find in your formula sheet, but in case formula sheet is not available, you can get that formula using this algebraic process shown here. Before we can use this formula, however, we need to convert the rate. The reason we need to convert the rate is because this annuity is general. Therefore, we have to go into step 1 of the process. Step 1 is designed to find periodic rate compounded monthly, which is equivalent to 3% nominal rate compounded daily. If you have formula sheet, you can right away use the formula from a formula sheet, but if we imagine that we do not have a formula sheet, we will invest $1 at 3% compounded daily for 1 year. And this future value of $1 invested at 3% compounded daily for 1 year should be equal to future value of $1 invested at some periodic rate I2 compounded monthly. These future values should be the same after 1 year, and that's the meaning of this equation. From here, we'll find, using algebra, I2, and that is equal to we used reciprocal exponent to exponent 12 to get rid of this exponent 12. So we divided 365 by 12. Here we divided 12 by 12. That's why exponent became 1. And we got rid of this exponent. Then we moved this 1 to the right side of this equation. You could use a formula and get this I2 right away. But if you don't remember that formula, you can use algebra to get to that result. So I2 is equal to 0.000250325. We need to make sure that we keep this I2 in the memory of the calculator in order not to type so many digits again. So now we are ready to go to step 2 of the process and find this n. N is equal here to logarithm. So future value is $50,000. The payment is $600. Then we'll multiply by I2. And I remind that I2 already is found and is stored in the memory of our calculator. Plus 1. And then we'll divide by a logarithm. 1 plus I2. And again, this I2 is stored in the memory of the calculator. Now we are ready to compute n. 75.78 rounded to 2 decimals payments. What this answer means is that we have 75 whole payments and 1 partial payment. 75 whole payments and 1 partial payment because we have here 0.78. Keep in mind though that this partial payment is not equal to 78% of $600. That will not be the case. But this is already a different story. What we need to know in this problem is that we in total have 76 payments, which is 6 years and 4 months. Here we go. The answer for this problem is that it requires 6 years and 4 months or 76 payments to accumulate $50,000. We'll use Excel now to find solution for the same problem. We will need first to convert the rate. Because remember, Excel's functions for annuity are designed for simple annuities. In order to use those functions, you need to first convert the rate. In order to convert the rate, you have to do 2 steps in Excel. First step is to find effective rate. To find effective rate, we'll use the function effect. This function calls for nominal rate first, which is in our cell B4. That nominal rate, which is known, is compounded 365 times per year, so we'll enter B3 into the formula. If I press enter, I see that effective rate is found here. Now I will need to use this effective rate to compute nominal rate. This will be the second step, which is required for Excel to go to nominal rate, which is equivalent to our 3% compounded daily. We need nominal rate, which is compounded monthly. So we'll use the function nominal in Excel. First comes effective rate. We'll have to use the effective rate that we already found in B7. And then we'll enter how many times we want our new rate to be compounded, which is 12 times. If I press enter, I'll find nominal rate compounded monthly, which is equivalent to 3% compounded daily. So once again, Excel doesn't have a process to find nominal rate right away. In Excel, you have to find effective rate first, which is equivalent to the original rate, and then you will need to find new nominal rate. Now we'll use this nominal rate to find N, which is the number of payments. In order to find number of payments, we will use function NPER, which stands for number of periods. First comes the rate. So we'll use this new rate because remember, this function NPER, like any other function which computes for annuities in Excel, is designed for simple annuities. Do not use this rate, 3% compounded daily here. Now, after you converted this 3% compounded daily into new nominal rate, which is now compounded monthly, annuity has become simple. Now you need to use this new nominal rate. So we'll use B8, which we have to divide by 12, because that's the new compounding frequency for the rate. And Excel requires periodic rate for rate. Next comes payment, which is in B2. We'll make this payment negative because payment is the amount outgoing. That's actually very important for Excel. In order for Excel to work properly, you need to make sure that you designate exactly which amount is outgoing and which amount is incoming. Next comes present value. In this case, we do not have present value because this is the problem about future value, and we don't have any investment upfront. Future value in this problem is $50,000, which is in B1. Next is the type of annuity. Either it is ordinary annuity or it is due annuity. This annuity is ordinary, so we'll select 0. If I press enter, I get my answer, which is 75.78 and so on, which corresponds to the answer we received in our algebraic solution. So the conclusion again is that it is 75 whole payments and 1 partial payment. In total, this means that we have 76 payments. But because payments are every month, so that requires 76 months. Converted to years and month, that is 6 years and 4 months. This finalizes the solution for this problem. Let's go ahead and consider the next problem. In our next problem, we need to determine the loan amount requiring 72 end-of-month payments of $400 if the interest rate is 5.5% compounded semi-annually. We also need to find the interest amount to be paid for this loan. Well, the payments are end-of-month payments, which makes this annuity ordinary. Also, it is important to note that we have monthly payments, but the rate is compounded semi-annually, which makes this annuity general. Because this annuity is general, we need to convert the rate to make this annuity simple. This will be our step 1. In step 1, we'll find I2, which is found in the following way. We can use this formula, 1 plus I1, M1 over M2 minus 1. I1 here is the known periodic rate. M1 is the number of times this known periodic rate is compounded. M2 is the number of times the unknown rate I2 is compounded. I remind that we can receive this formula by comparing $1 invested for 1 year at the known rate and the unknown rate. The future values after 1 year should be the same. We can build an equation and find this I2. Substituting values, we'll find I2 now. 1 plus I1, which is 0.055 over 2 over 12 minus 1. So once again, 0.055 over 2 is the periodic rate, which is the known periodic rate compounded semi-annually. 2 is the number of times that known periodic rate is compounded, and 12 is the number of times the unknown rate must be compounded. We are ready to compute it now, which will be 0.00453168.2. We'll keep this value in the calculator and proceed to step 2. In step 2, we will need to use present value. It is present value because we are talking here about the loan amount. We take the loan in present and then we pay those periodic payments later. That's why we need present value of annuity formula here. This formula is this: present value equals to PMT, and we'll have a fraction 1 minus 1 plus I, exponent is minus n over I. Once again, I here is the periodic rate, n is the total number of periods, PMT is the periodic payment, and PV is the present value, of course. We can use this formula right now because our annuity has become ordinary simple annuity. I remind you that this formula can be used only if you deal with ordinary simple annuity. But we could convert the rate in step 1 and make this annuity ordinary simple. PMT is $400, 1 minus 1 plus. Periodic rate is going to be I2 this time. We actually found this I2 here. We'll use this I2. It is in the memory of our calculator, so we don't need really to write this long number here. Note that we already are given N as 72 end of month payments. So N is going to be 72. Because it's present value, it's negative sign in the exponent, divided by I2. Now we are ready to compute this using our calculator, and the answer will be 24,526.49, rounded to 2 decimals. Now we are ready to find interest amount. Because interest is included in periodic payments, we will need to find all periodic payments combined, so PMT times N, and then we'll subtract from this amount the present value. Each payment is $400. We'll multiply this payment by 72 payments, and we'll subtract present value, which we found 24,526.49, which will result in 4,273.51. Thus, we found interest amount and present value, which is the loan, for this problem. Now we'll solve this problem with Excel. First, because this is a general annuity, we need to convert the rate. In order to convert the rate in Excel, you need to find effective rate first. This is done with the function effect. This function calls for the nominal rate, which is the nominal rate given in B3. Number of periods that rate is compounded is going to be in B4. As a result, in B6 we have effective rate, which is equivalent to 5.5% compounded semi-annually. We'll use this effective rate now to find nominal rate, which is going to be equivalent to 5.5% compounded semi-annually, and which is going to be compounded monthly. In order to find it, we'll use the function nominal, which calls for effective rate, which is going to be in cell B6, and the number of times that new nominal rate needs to be compounded is 12. Thus, in B7, we found nominal rate, which is equivalent to 5.5% compounded semi-annually. I remind that Excel can find equivalent nominal rate only through effective rate, which is why we have found effective rate first. After we found this nominal rate, annuity has become simple, and we can compute present value. Excel's functions for annuities are designed for simple annuities. Therefore, you always need to compute equivalent rate and make annuities simple if you want to use Excel's function. After we activate the function PV, first comes the rate, which is always periodic rate in Excel. This is going to be here in B7, but we need to divide that nominal rate by 12 to make sure that we find periodic rate. Number of periods is given already in B2. That's 72 months. Payment is in B1, but we'll make that payment negative to signify that this payment is an amount outgoing, because we want our present value to be displayed as amount incoming. Future value is going to be 0, because we want nothing to be left of the loan. We want to pay that loan completely. Finally, this annuity is ordinary, so we'll select 0 for end of period annuity. If I press enter, I have my answer, which is 24,526.49. Let's find interest now. Interest is equal to all payments combined, which is found by taking B1 and multiplying by the total number of payments, which is in B2. We'll subtract from this the present value, which is in cell B9. Thus, the interest is 4,273.51. These are the answers we already received with our algebraic solution. Let's proceed now to the next problem. How many years and months are necessary to pay off a loan of $40,000 if $500 is paid at the beginning of every month at 8% compounded semi-annually? $500 is paid at the beginning of every month, which makes this annuity due. Then the payments are done every month and the rate is compounded semi-annually, which makes this annuity general. So we have due general annuity. Let's convert the rate first, because that's a general annuity. We will convert the rate right now by using the formula for I2. 1 plus I1, M1 over M2 minus 1. I1 is the periodic rate, which is the known periodic rate. M1 is the number of times the known periodic rate is compounded. M2 is the number of times the unknown periodic rate I2 is compounded. I2 is equal to 1 plus 0.08 over 2, 2 over 12 minus 1. I2 is equal to 0.006558197. With this I2, we are ready to proceed to step 2 of the problem. In step 2, we need to find n. Let's remind ourselves the formula for present value for due simple annuity. Present value equals to PMT, 1 minus 1 plus I, exponent is minus n, I. And then this is also multiplied by 1 plus I. Because this annuity is due annuity, there is this term which we have to multiply by. We'll use this formula to find formula for n. This is found pretty easily by using algebra. We'll start with present value. We'll divide it by PMT. Then we also will divide it by 1 plus I. And then we'll multiply by this I. What will be remaining is 1 minus 1 plus I minus n. Then we'll use some algebra to move 1 plus I exponent minus n to the left side to get rid of the negative sign in front of it. And then we'll move what is now on the left side to the right side. So it will result in the following. We can use logarithm now on both sides, and we'll use logarithm rule, which makes exponent minus n coming in front of the logarithm as multiplication. So it will be minus n times logarithm 1 plus I. And on the right side, we have also logarithm 1 minus. I'll write this PV times I, like so, divided by PMT 1 plus I. Finally, we are ready to receive our formula, which is going to be n equals to minus. So this minus will now go to the right side of the equation, and there will be fraction involving logarithms. This is the formula for number of payments given present value and given due annuity. This formula can be readily given to you in a formula sheet, or you can simply remember this formula. But if you don't have access to a formula sheet, or if you don't remember, but if you know some algebra, you can receive this formula from the original formula for due annuity. Now we are ready to use this formula to compute n. We'll do it here. N is equal to minus. We'll substitute values now. Logarithm 1 minus. Present value for this problem is 40,000. Times periodic rate is going to be I2. We already found this I2. Divided by payment, which is $500, times 1 plus I2, and divided by logarithm 1 plus I2. Remember again that I2 is already found by us, and it's in the memory of our calculator. Now we need to compute this n very carefully in the calculator. 112.68 payments. We need to remember that payments are happening at the beginning of every month. When we found 112.68 payments, this means that there are 113 payments in total. 112 whole payments, and there will be also one partial payment. However, because this is a due annuity, we're talking about 112 months. You have to be careful when finding time for present value of due annuity. We can demonstrate it by taking an example involving only 2 payments and involving present value of due annuity. Let's have the first payment today and another payment is in 1 month from today. So this is today times 0. We have plus first month, 1 month ahead, and then plus second month. You see, there are 2 payments here, but it's only taking 1 month to make those payments, because this first payment is happening today. It doesn't count towards time. Therefore, when you find time involving present value of due annuity, you need to find the number of payments first, then you will need to subtract 1 from that number, and you will get that number of time periods involving present value of due annuity. I'm speaking about present value of due annuity because for future value of due annuity, that's not the case. When you have future value problem, it means that you have an accumulation process. So after the last payment of the due annuity involving accumulation process, you still need to wait 1 period until that accumulation process is complete and you reach the necessary amount. Therefore, when you have a problem for finding time for future value of due annuity, you will find the number of payments first, that number n, and that number will coincide with the number of time periods. You will not have to subtract 1 from the number of payments to get time. We found that there are 113 payments in this problem, but actually in terms of time, it takes 112 months to pay for this annuity. In terms of years and months, we're talking here about 9 years and 4 months, which are required to pay for the loan of $40,000, subject to the conditions of this problem. Let's consider Excel solution. In Excel, we have our values entered already. Because that's a general annuity, we'll start with effective rate. It is the function effect. First comes the known nominal rate, which is B3. The number of times this known rate is compounded is given in B4. We found the effective rate. It's 8.16%. We'll now find nominal rate. This is given with the function nominal. Effective rate that we found is in B6. Number of times we want this nominal rate to be compounded is 12. With this nominal rate, annuity has become simple annuity, and we'll now use function NPER. NPER stands for number of periods. We'll use the rate first. It is in cell B7, but we remember that Excel requires periodic rate, so we divide it by 12, since this new nominal rate is compounded monthly. PMT is given in cell B2. Let's make it negative to signify that this is the amount outgoing. For Excel, it's very important to distinguish amounts incoming and amounts outgoing. Present value is given in cell B1. So notice that I made PMT negative, but present value I made positive. So that's very important to distinguish between amount incoming and amount outgoing, as I already mentioned. Future value is 0 because in this loan nothing remains. And we'll select beginning of period because that's due annuity. Let's compute it. It's going to be 112.68. Exactly the same answer as we found in our algebraic solution, which results in 113 payments. However, in terms of month, it's 112 months for reasons I already explained. This finalizes the solution for this problem. There are 60 beginning of quarter periodic payments that are required to pay off a car priced $67,000. If the effective rate on the loan is 3.2%, how much is each payment? In this problem, we have a due annuity because these are beginning of quarter payments. Also, payments are happening every quarter, and the rate is effective, which means that it's compounded annually. Because the rate is compounded annually, and because payments are quarterly, we have a general annuity. Thus, we have due general annuity. To solve it, we first will convert the rate, which is to find I2, so it's going to be step 1. I2 is equal to 1 plus 0.032. It would be divided by 1 here because that rate is effective rate compounded annually. I don't write division by 1 here because dividing by 1 doesn't change the number. The exponent is going to be 1 over 4 because there are 4 quarterly payments. We're converting 3.2% compounded annually to a rate, I2, which is going to be periodic rate, but compounded quarterly, minus 1. I2 therefore is equal to 0.00790575. Once again, this I2 is periodic rate compounded quarterly, and this periodic rate compounded quarterly is equivalent to 3.2% compounded annually. Therefore, with this new I2, our annuity has become simple due, and we are ready to proceed to step 2. For this simple due annuity, we can use the formula for present value of due annuity, and we'll use this formula then to find the payments. Let's remind ourselves how this formula looks like. Present value equals to payment, which is the payment associated with the due annuity, multiplied by the fraction. 1 minus 1 plus I, exponent is minus n, I is in the denominator here, and then we have this additional term 1 plus I. Every time when we have due annuity, we should always multiply our formula for simple ordinary annuity by this additional term 1 plus I. Now we will substitute values, and from there we'll be looking for PMT. Present value in this problem is 67,000. PMT is unknown, so we'll keep it as just PMT here. Then we will be substituting our values, 1 minus 1 plus I2, where I2 is what we already found, and the exponent is going to be minus 60. In this problem, we already have the total number of payments given, 60. Negative sign here is because that's present value formula. And we will divide by I2, again the same I2 we already found, and we'll multiply by 1 plus I2 here because that's due annuity. What is left for us to do is to compute this part first. Let's compute this part on the right. Let's call this part underlined with red color by some letter A. PMT will be equal to 67,000 divided by this A. When you compute this A in a calculator, you should be careful to make sure that you keep all decimals for this A. So now let's go ahead, carefully compute this part in the calculator, then we'll use this part to compute payment. Let's see what we get. This is equal to 67,000 divided by 48.00588,572. So this number in the denominator is the A which I found here. Now, if I compute this, I'll get 1,395.66 rounded to 2 decimals. Thus, we found that each payment is 1,395.66. Let's try to solve the same problem with Excel. In Excel, we need to convert the rate first because that's general annuity. We already have effective rate here, so we'll use function nominal to use this effective rate. So nominal function calls for effective rate. It's here in cell B3. Number of periods that we need is going to be 4. That's because we need quarterly compounded rate. Thus, we found nominal rate. This nominal rate compounded quarterly is equivalent to effective rate of 3.2%. With this nominal rate, we are ready to find PMT. All functions which are annuity functions in Excel are designed for simple annuities. Now, after conversion of the rate, this annuity has become simple annuity, and we are ready to use this function. The function we need is going to be the function PMT. First, it calls for the rate. The rate is in cell B6, which we need to divide by 4 because it's a quarterly compounded rate and we need periodic rate in the function. Then comes number of periods. It's already given in cell B2. Then we need to enter present value. It's going to be 67,000, which is given in cell B1, but we'll make it negative because we want our PMT to be displayed as positive. I remind that Excel distinguishes between negative and positive values. So if you entered B1 here as positive number, PMT would appear to be negative number. Future value is 0 in this problem because we want nothing of the loan to be remaining. Finally, we need to select either this annuity ordinary or due. Of course, this annuity is due. That's why we'll select 1 for this function. If we press enter, we receive our answer, 1,395.66, which is exactly the same answer we received with using algebra. That finalizes our problems for this video.